My assignment was to design and grow an efficient network using the Physarum polycephalum. This assignment was probably a bit different than most of yours. There was much less code involved, and the major difficulty was learning how to effectively culture this organism and how to design a network that best uses natural assets. Physarum polycephalum means the many-headed slime. Many people refer to it as a slime mold, but it's not a mold. That's a relic of its old classification among the fungi. But fungi do not move, and this organism does. So it's since then been moved to the protist, but the name is retained. Physarum polycephalum is commonly used in biocomputation problems. The reason for this is that it was discovered it could solve shortest path problems. The first of which was a maze problem, in which a piece of food was placed on one end of the maze, with many avenues to get to that food. And on the other end was the organism. The organism then spread out to cover all the avenues of the maze to find the food, or other food if they existed. Once it did find the food on the other side of the maze, it retracted its influence in the other avenues, but in addition to forming a strong network with its veins through the shortest path to get to that food. This makes sense biologically, that an organism would find the most cost-efficient route in the wild to food, given that it does not know when it will next eat. Another problem that this organism solved that was interesting to biocomputation was a network problem. The organism was placed randomly on a map that resembled the Tokyo surrounding. Nodes were placed on train stops around Tokyo and the surrounding cities. What ended up happening was the organisms spread out to all the food nodes that were placed around Japan, and it formed a network between all those nodes that mimicked the efficiency of the existing Tokyo Railway. So what this demonstrated to researchers was that this organism does have the ability to design efficient networks. Now, it should be noted that the networks it's designing are a form of simple single-cell intelligence. It's not necessarily that the organism is thinking about how to make this network as efficient as possible, as an engineer might when designing something like the Tokyo Railway. But it's still interesting that it can produce such similar results to what humans can do without the time that you need to spend engineering such a problem with humans. So I have what remains of my test experiment of this organism. Unfortunately, I can't demonstrate the plasmodial stage, which is the active feeding stage of this organism. This organism actually has two states. It has a plasmodial state in which it feeds and actually forms the networks, and a sclerotium state in which it hardens and retracts so it can survive harsh conditions. This is what the plasmodial state looked of my organism at its peak. This took about 3 weeks of growth. You can see here, this is where I brought the organism in from the petri dish that I purchased it in. I simply just moved it from its original culture and then cultured a new one here. If you're wondering where those nodes are placed and why I did that, I designed this structure, this network, around locations at our school. So here is the map that I used as a reference point to design a network for. The dots, vertices in this graph, represent points of interest, and the food nodes on the actual environment that it created for the Physarum polycephalum are represented by these dots. So here we can see it again after looking at what the map was. Those yellow lines are the network veins that the Physarum forms between nodes. They're protoplasmic in nature, and they contain many nuclei. It's a single-celled organism, so it's meaning that the organism that started here is the same organism over here and spread out across all these network veins. Now in real time, you can see that those network veins are gone inside in this Tupperware environment. That's because all the nutrients are gone from these oat flakes, these food nodes. What remains is the sclerotium of the Physarum polycephalum. So it's still alive right now, but it's hardened and is preparing for potentially starvation. The organism can actually be easily collected in this state and brought back to life using more food. I may do so later when I'm doing another experiment, potentially with a maze. But for now, it's safe to store this, and it will last probably a year or a few years. So once I grew this network and I was satisfied with the state of the Physarum polycephalum's growth, I was able to process this image to get the exact lengths of these network veins. The reason why I needed an image processor for this was that it's difficult to tell what the exact length of one of these networks are. They're not straight and they do a lot of curves. For reference, I added a ruler here at the bottom to measure this in millimeters. I chose millimeters because it would be a more interesting measurement with whole numbers rather than every number being some decimal form of 1 or 0. It's important to measure the length of these veins using a consistent ruler, because if you wanted to, say, scale this up to meters and actually measure the distance that would be represented on the actual school, you need that consistent real life ratio. So this is an example of the workstation I was using to process the image. Here we have a list of the lengths of the network veins. As you can see, I wasn't finished by this time I took this photo, but there's a lot of different lengths that represent, the length being in millimeters, that represent these networks. So here is a abstract representation of the Physarum network. The lines are straight because it doesn't necessarily matter that I draw them as curvy, because I have the lengths. And in a weighted graph, that's what matters the most, are the lengths. So it's a bit difficult to see from this image, unfortunately, through this video. But this is the same, mostly the same layout I tried to get of that image, just with straighter lines and easier to manage edges. Because this graph was weighted, I was able to do a few interesting computational problems in graph theory. So this is a shortest path algorithm. It used Dijkstra's algorithm. It finds, based on edges, the shortest path through this network. It's hard to tell on this image, but it's the highlighted blue line is the shortest path that touches all nodes in this graph. You can reason for a purpose for this algorithm used in this particular network, because say you're designing a school or designing something maybe that has thousands of nodes and not just 22 like mine does, and say that you didn't want to waste the time on a human drawing potentially all the shortest paths through randomly placed nodes. So you grow a Physarum polycephalum, and it spreads out and does all the work for you reasonably efficiently. And then you can do algorithms like this. You can solve problems like this with actual human time and utilizing human assets, while you let the Physarum polycephalum utilize its natural assets of forming efficient networks. Here's another problem solved. This is a minimum spanning tree, it's slightly different. It's a similar concept in which it must touch all nodes, but it actually forms a different subtree using this method because the criteria is different. Here's a vertex clique. So this is a clique of vertices or food nodes in the actual Physarum graph that have the most interconnectedness with them. This is a maximal clique, so this is the maximum amount of nodes that are all connected with each other. This could be useful in an engineering problem because the Physarum is not thinking about how to optimally design its network for human use. So if you imagine this is a location in the school and an advertiser wants to set up somewhere where the most people will be walking by, it might be reasonable to assume that this maximal clique is the area that most students will be walking by because it's the most connected area. Additionally, you could probably remove some of these edges, save some money on some of these roads if you were to just take it out, because those nodes are so connected already that you could get there by taking other routes. Another important issue solved with doing these little graph problems like minimum spanning trees is that you can find out what the most cost-effective route through the graph is. So since this is a weighted graph, this path right here is the least cost route through the graph that touches all the nodes. So if you were say engineering a road for this school and you needed to build something and you needed to build at least a path right away, the best idea would be to build the cheapest path through all the nodes in the school so that you could reach everywhere, and then you save money and you can build the rest of the paths later. Overall, I would say that this project was very interesting, and while I did it alone, I think that was partly due to the fact of it seemed like this project would cost a lot of money to get the organism. This is actually not true, and if you're listening, Dr. Ravi, this project was fairly inexpensive by doing it on a budget. So the major expense from this project, at least looking online, is buying a kit to grow this organism. You actually don't need a kit. You only need a paper towel for the substrate, which it actually works. It's a damp paper towel, wringed out of all the water, of course, because you don't want the organism to drown. Oat flakes to feed it. Tupperware, sealed Tupperware to contain it. This Tupperware is a little too nice for this because I ended up taking it off the cover to take pictures of it. It was difficult to take a picture through here and get, this Rubbermaid logo is in the way, and it was difficult to actually measure the edges, the network veins, through this container. So I took it off anyway. So you can even get away with a cheaper Tupperware container, probably about $1. And then after that, so most people have Tupperware with them. Most people have oat flakes. Most people have paper towel. So that's negligible in cost. The next is getting the organism. And the organism, if you purchase a small sample of it, a small sample of an active plasmodial feeding culture, it's only about $9 to $10. So most of the kits cost around $50 to $60 to $70, but you can get away with just spending about $10 to $13 on this, which I think is completely reasonable for something as interesting as growing your own network, doing an experiment with a biological organism, which I think is always valuable and is always something different, and it'll be easy to tell, future employers or friends in the future about how you designed a biocomputer, essentially. So if you want me to send you a link to all the locations I got my resources from, I'd be happy to. Just let me know. I think future students would find this to be very satisfying. It does have a long ramp up time. It took 3 weeks to grow it, and I was worried that it wasn't going to grow when I checked on it after the first week. It does need to be sprayed with water, a very small amount of tap water daily to keep it moist. But you can't spread too much because you don't want it to drown. Other than that, it doesn't need much work while it's doing that growth process over 3 weeks. Once it's finished, you just take a picture of it, and then you can let it do whatever it wants. You could move it to another area to culture another experiment. You could leave it like I did and form sclerotium to work with later. Um, and then from there, you can process your image. You can demonstrate your graph. So it didn't mention this, but for an organism without a brain, this graph seems pretty reasonable in terms of efficiency. The nodes are more or less in the same location that I placed my oat flakes in, and I'd say this was a successful experiment as a result. Um, I wasn't gonna say I'm surprised that it was gonna work like this because I expected it to. I did a lot of reading on this beforehand, and a lot of people work with this organism, so it was easy to find that it is the real deal. It's not something that it's gonna work half the time. And yeah, I hope to work with this in the future. Uh, if anyone else wants to work with it too, just let me know. I consider myself pretty well versed in this organism now, so thanks.